Hello and welcome to this introduction to Spark SQL. I am Luca Canali with CERN IT, Data Analytics and Spark Service. Spark has two APIs for the same functionality, Spark SQL and the DataFrame Declarative API. We can see here in an example running PySpark that we define a data frame with numbers from 0 to 9. And then we count the data frame, and we have 10 rows as a result. Using Spark SQL, we can express the same computation using spark.sql and a SQL statement where we select ID from range 10 to define the data frame, and then we have df.count to count again the number of rows into the data frame. This is what the data frame looks like. And these two ways of expressing the computation with DataFrame Declarative API or with Spark SQL are equivalent for the execution of the task. So why would you want to use SQL? So this is for if you already have a SQL application, if you're already familiar with SQL. Also, you can consider that Spark implements a quite complete set of SQL statements, as we will see, and then certain computations can be more naturally expressed in SQL. This is a matter of taste. For example, I like to express joins using SQL, but they can of course be very well expressed using DataFrame Declarative API. Why would you want to use the DataFrame API instead of the Spark SQL on the other side? DataFrame API is a modern API similar to Python Pandas. You may be familiar already with Python Pandas, or you may be porting applications written in Pandas or using other data frames. So in that case, maybe it's more natural to use the DataFrame Declarative API. Sometimes the DataFrame API is an obvious choice. For example, if you just need to count the number of rows in a data frame, you can just do .count. Another possibility is that when we want to build queries dynamically, suppose this in a program. Let's say we have a variable that if it's greater than 0, we want to filter the data frame with a filter on column 1, otherwise a filter on column 2. We could express it with something like that in Python. So when we have data frames and we want to operate with Spark SQL, we need to map the data frames into tables and views. One way to do that is to use the create or replace temp view method on the data frame. And we will see an example here. We create a data frame. Normally you read data from files, but here we create it directly from the command line. We have an ID and a name, which is a number and a string, and we map the data frame to a temporary view called My Events. And then we just select the number of rows from this temporary view. Sometimes you need to go the other way around. You have a table or view and you want to have a data frame, because then maybe you want to continue the processing with the DataFrame Declarative API. So you just use spark.table and the name of the table, and then you get a data frame out of it. It's very important to note that no data is being copied. These are just operations that are internal to Spark. So some of the key operations that you want to do with structured data with DataFrame API and SQL are selections, projections, joins, unions. In general, you want to use these components to describe computation, and you don't need to tell Spark how to perform the computation. You just express the result in terms of these categories of operations. Spark will find an optimized way to execute your SQL operation. Spark has an optimizer for this type of operations. It's called Catalyst and generates as an output optimized physical plans. So we start, for example, with data frame operations or with SQL, abstract syntax trees, and then goes through Catalyst, and as an output would be a set of executions with using the underlying engine of Spark that is using RDDs. We will not cover RDDs in this course. We will focus on the DataFrame API. So Catalyst, what it does, it will take it will first generate an unresolved logical plan, and then it will refine it into multiple logical plans, and finally we come up with a physical plan, and maybe even optimize it further if we are using table statistics, for example, using a cost model. And at the end we have a selected physical plan. This will tell Spark, go and read that particular file, do this type of join, and write the results into those other files. So physical operations. An example of execution plan, and now you can get an execution plan for your DataFrame operations, is using the fexplain or SQL explain select. We will see in one of the demos a table called movies containing a list of movies where we have movie ID and title, and here we apply a filter onto it, and then we get explain. So one operation that will be done is reading the CSV, because that's where data for this table is, and then a filter is applied. The filter on movie ID equals 1. So it's important to remember that Spark uses lazy execution. So Spark SQL and DataFrame API will describe the computation, and then there will be a series of transformations, and then there will be an action that will finally trigger execution. First, the optimization of the all operations that needs to be run, and then the final execution. Typical examples of actions are count, show, collect, and also write to file system. For example, we want to write the final data frame into a set of files. Some basic examples of Spark SQL are these. Let's first create a test table with a similar but slightly different syntax from what we have seen before. Here we're using this select from values, the values keyword, and then we give the values that we want to have. So these are 3 rows, and then the columns that will be ID and name. And then we map it to a temporary view called T1. The first one just selects the 2 columns and creates a 3rd column, which is computed from an expression. And then with show we can see the data. In the demo we will run this. Another operation adds a filter where ID less 3. And a 3rd example will just do some group by, where we can count the number of samples and we can sum them. So an increasing order of complexity. So joins are very important operations in all databases and data processing engines. And it's very important that the system that we are using to run the joins can run joins on large tables, and it can be optimized, and this can make quite a big difference. In particular, it's important to select the correct algorithms for the joins, and also the order of the joins for the tables. So a bit of a refresher on joins. Here we have 2 tables, employee and department, with a relationship 1 to many. So an employee is in one department, and one department can have 1 or more employees. And then we have a select, where we select the employee ID, the name, and the department name. And we get this information from 2 tables, so we need to join employees and departments. And there is a joining expression, which is the department ID on employees is equal to the departments.id. I want also to emphasize another type of join that is called the outer join, with a small difference. First, the syntax is left outer join. And this, as we will see in the demo, requests the system to print all the values for the table departments, even if there are no matches. In that case, this is matched with a null value on the employees tables on the right in this case. So joins execution in Spark. The Spark optimizer catalyst will find a suitable execution plan for you, and the Spark engine will run it in a fault resilient and parallel way. And there are 3 main methods that I want to mention for joining in Spark: short merge joins, shuffle hash joins. These 2 are used for joining large tables, and broadcast join, which is a very interesting optimization that is highlighted here. In broadcast join, we have a small table that is joined with a large table. where small is a configurable value. By default is 10 megabytes. Let's say the table is 10 megabytes or less. Then it's broadcasted to all the executors in the cluster and is joined against partitions of the large table. And this performs better than the other methods when one of the tables is small and the other one is large. Spark can also read from relational databases. For example, we have Oracle and relational database services at CERN. And this is the way you can access data in a database from Spark. You use JDBC data source, and then you will need to specify the connectivity details and the driver that you're going to use, and then what table you want to access or query that you want to run, and then a user password, and also other optimization parameters like the fetch size, so how many rows at a time you want to get. And so this will define a data frame that goes and reads from Oracle, and we can see the schema, and when an action is triggered, this will go and fetch the data from Oracle. I want to show now some example SQL that it goes beyond the basic one that we have seen so far. I will start with a demo, with an example that we'll see also in the demo later on, of FitzBuzz, which is a typical training exercise. This illustrates the case statement. Case is something you may be familiar with from procedural languages, allowed to switch executions, branching it depending on conditions. And this allows to run the FitzBuzz demo. So case will say, for example, if the ID is a multiple of 3, then you print Fizz. And when we put this all together, we get all the numbers, 1, 2, 3, then there's Fizz, and 4, then is Buzz, because it's a multiple of 5, etc. This to show that SQL can be complex, can have very powerful statements that allow also to go beyond the typical set operations that one does with SQL that we have seen in the basic examples before. So more SQL here for complex analytics. These are window functions, quite a specialized topic. They are available in many databases and data systems. They are also available in Spark and allows to run complex reports. Just an example here, we will see the output of it in the demo later on. So we query from employees. First we query the ID, the name, and department ID, so standard columns. And then we want to answer questions like, what is the greatest ID given the same department, where same means the same department of the given ID that is being printed, row by row. And we can use the function max, and then the special syntax over, and then partition by department ID. And also we have a possibility to see the name of the previous employee, so the employee who was hired before the current one that we are displaying now. As I mentioned, if you haven't seen this, we will see the results in the demo later on. Spark SQL and Arrays. So arrays are very complex and difficult to process using SQL and systems that process structured data. Spark has some optimizations to work with arrays and complex data types. Here we see an example where we have a schema with an ID, which is an integer, and then it is an array. Here we are representing a system where we have temperature readings that are integers, and we have 2 rows in the demo schema. We can create the data frame like this and then map it to a temporary view. And then when we select the data from it, we have the ID, which is just a number, and then the temperature Celsius is a column containing an array of numbers. So we can do some processing. In particular, there are some array functions, but here I want to, in Spark, but here I want to mention the Spark higher order functions that allow to do some complex computations. For example, let's say we want to multiply by 2 all the values in the arrays. We can do that using a transformations where we transform all the values in twice the value using this type of syntax. We will run this in the demo. We'll have also more examples of array functions in Spark. The next is again with higher order functions, and here we show a filter similar to what we have seen before. That was a transformation. Yeah, we want to filter, we want to have high temperature values defined by T greater than 38. So the results will be smaller arrays than the input, where only the filtered values are displayed. We can have complex schemas in Spark. This is inspired from physics. Let's say we have a list of events, and then there is a struct with some flags for a high-level trigger. And then we have a list of muons, and for each muon, we have certain characteristics of the muon that are used by analysis. Okay, when all the standard SQL functions or the complex ones or the array functions are not enough, you can extend Spark functionality using user-defined functions. And you can write them in Scala or Python. Here we see the Python version. So this will be executed by Spark that runs in the JVM by spawning Python workers, and then the code and data will be sent there. This is a way to do it. It's you first import UDF and then define a UDF with this decorator. This is a simple one. We just have a sleep of 1 second to simulate some complex processing that may be done by the UDF, and we just return 2 times the input. We need to register this UDF to be able to use it with SQL, and then we can experiment with it. We selected a slow function from 1. This will just work on 1 row, and this will work on 10 rows. We will see in the demo what this gives. There is a faster implementation of Python UDFs that are called Pandas UDF that have improved performance. They have a similar architecture for what we've seen before, but this time the serialization and deserialization will work in batches of 10,000 rows using Pandas series and using PyArrow. So PyArrow is the serialization mechanism used, and the data will be shipped and received as Pandas series, which allows to write the UDF working on a Pandas series on chunks of data, which gets some array processing basically, which speeds up the operations. So it's not applicable to all cases, but when it is, it improves the performance. Here we have the example where we define the Pandas UDF, multiplying 2 values. We need to register it again to be able to use it. And then this is executed on 1, 10, or 10,000 rows. We will see in the examples the performance difference between these 3 and compare it to the normal UDF. Using modern Python, Python 3, which is now common, you can also use annotation hints, which will make more clear the fact that this data will be sent over as Pandas series, and also the results will be a Pandas series. And it's also possible to use another syntax where the UDF will be defined using iterators, which is useful when you have a state initialization that can be a very expensive operation, like for example loading up a machine learning model for serving it. So this brings us to the end of this module. I would like to emphasize a few key learning points. So the first one is the DataFrame API and Spark SQL are 2 interfaces to the same execution engine in Spark. Both of them are powerful abstractions for processing structured data at scale and in a fault-reliable manner, and are extensible using user-defined functions that you can write also in Python.